And now we get to talk about psychological science. Welcome back, one and all. We're going to be talking about research methods, statistics, all the most fun stuff that I know all of you signed on to this course to learn about. You're like, yes, independent variables. There it is, that word that I said that I would keep using. There it is again. Dependent variables. Yes, I can't wait. Science. It worked. So let's go through the things we need to go through. Here's a reminder. If this were actually a class that was in person, background noise is my cat, there would be a no cell phone policy. That doesn't apply right here. You could be watching this on your cell phone for all I know. The required texts are Introduction to Psychology, which is open source, and there's a link to it, as well as 7.5 lessons about the brain. Now, for this week, you were to have read chapter 2 of the textbook. That's the open source one, the open access one, as well as the half lesson from 7.5 lessons about the brain. I will have a separate video for 7.5 lessons, for the half lesson of 7.5 lessons about the brain. And so it won't be incorporated into this lecture, but it will be incorporated into the next lecture. I'm sorry, as its own video, and it's going to make sense in the next lecture, which is going to be about biology. Let's take a look. Biology, brains, bodies, and behavior. I threw in the word biology, but that's really what it's about, biological psychology. So here we are covering the material for the week of September 19th, 2022. Best day in the world, Christember. And do you even science, bro? I know not all of you are bros, but I'm gonna utilize the term. I'm gonna hijack it because it's funny. And it demonstrates the problems with bro science. As compared to bro science, we actually science, bro, in the realm of psychology. Okay, so is psychology a science? The answer is yes. In fact, psychology can be thought of as the most sophisticated of the sciences because we deal with human variability. As a result, psychologists have developed procedures and statistical methods for dealing with this variability scientifically. Let's start from scratch. Here's the outline we're going to be using for this lecture. I might break this up into chunks. We're going to start talking about the scientific method, or what I was going to call it a bumper sticker, but it has way too many words, but it is the super fantastic way to answer any question about the natural world, including human behavior and experience. Which, if you remember from the What is Psychology lecture, is the definition of psychology, the scientific study of human behavior and experience. We're going to break this down into talking about hypotheses and theories. Might be a little bit different than you think or how you use them in normal conversation. There are technical definitions. We're going to talk about populations and samples. We're going to talk about research methods as well as statistics. The ability to replicate a study that's already been done. That's called replicability. And then we're going to go over some ethical concerns that go into testing human or non-human animals, because psychology does both. If you remember from the history of psychology lecture, we talked about Charles Darwin and how his theory of evolution opened up the idea of humans being animals. So why not study other animals to learn more about humans? Sounds like a good research protocol, but there are ethical concerns. The word science derives from the Latin word scire or scientia, roughly meaning knowledge. And we will define it as an organized collection of facts that explains relationships between variables. Say that one more time. Science, for the purposes of this class, is an organized collection of facts that explains relationships between variables. Proper sciencing, and that's not really a word, please know that, uses the scientific method. Scientific method, we're going to define as the process by which facts are collected, analyzed, and interpreted. This is used by psychologists to look at human behavior and experience, hence making it the science of psychology. It's also known by some as the super fantastic way to answer any question about the natural world, including human behavior and experience. But before we get deeper into the super fantastic and how it's used in psychology, let's be honest about how psychology is different from other scientific fields. For starters, there's the history. Other sciences began gradually from the work of amateurs. Psychology, in contrast, began in Leipzig, Germany in 1879, first psychological lab founded by Wilhelm Wundt, and it was founded as a deliberate attempt to start a new science by people who are already scientifically trained in related or medical fields, applying the methods of the natural sciences to questions of philosophy and the mind, right? So psychology, like, we know when it started, and just to beat it into y'all's heads, it started in Leipzig, Germany in 1879. Wilhelm Wundt, Leipzig, Germany. Another thing that makes psychology different from other fields of science is the ethical concerns that the environment of psychological testing exists in. So since psychologists deal with other humans and sometimes non-human animals, there are many protections in place and therefore rules that need to be followed to ensure the safety, health, and protection of research subjects. I will have more to say about the ethical concerns at the end of the lecture. In case you didn't see that, it's the 6th out of the 6 points. But know that other scientists, like physicists or geologists, they have concerns, but they don't have these kinds of ethical concerns because, of course, physicists, maybe if they're cosmologists, they're dealing with planets that are far, far away, or if they're geologists, they're dealing with inanimate objects. And they just have different concerns than psychologists testing human and non-human animals. Hopefully that's obvious. Now, let's start talking about hypotheses and theories. And we're going to use an example that is in your open access textbook. So in your open access textbook, they talk about an Anderson and Dill study from 22 years ago, from 2000, asking the question, does playing violent video games increase aggressive behavior? So this, again, this example is in your textbook, but I'm gonna do it like story time. There's the camera. So consider an experiment conducted in 2000 by Anderson and Dill. The study was designed to test the hypothesis that viewing violent video games would increase aggressive behavior. In this research, both male and female undergraduates from Iowa State University, I'm imagining that's where Anderson and Dill teach at, were given a chance to play with either a violent video game, and by violent, they considered, I am not a gamer, so I'm just going to assume that those of you who are gamers know what this means. Wolfenstein 3D, let's assume that's a game that is violent to some. And then there's a non-violent video game that others played, and that was Myst with a Y, M-Y-S-T. I know I sound so old talking about these video games that are themselves already 22 years old. I bet this is a joy to listen to. All right, Here we go. So during the experimental session, the participants played their assigned video game, either Wolfenstein 3D, violent, or Myst, which was non-violent. They played it for 15 minutes. After the play, each participant played a competitive game with an opponent in which the participant would deliver blasts of white noise through the earphones of their opponent. So the operational definition of the dependent variable, which is aggressive behavior, the sentence is going to make sense in a little bit. The operational definition of the dependent variable, aggressive behavior, was the level and duration of noise delivered to their opponent. So they were considered more aggressive if they delivered a higher level, longer duration white noise into the earphones of their opponents. Let's review. You play either a violent or a non-violent video game. Afterwards, both groups, people who have the non-violent game and the violent version of the game, both of them then play a game where they get to blast opponents with noise in their ears. All right. Now we want to see, is the duration and level of noise in one group different than the other? Because if it's higher, it's going to be interpreted as more aggressive. And according to Hypothesis, they're expecting the people who play the violent video games to show an increase in aggressive behavior. All right. Now that was fun. So keep that in mind. Keep in mind the idea of violent video games, aggression. We're going to keep playing with those as we keep going. Let's start with hypotheses and theories. Make sure you understand the terms being used. How can you understand an experiment or its results or how it was done if you don't understand the definitions of the terms being used? Operational definitions are a precise statement of how, a precise statement of how a conceptual variable is turned into a measured variable. So these definitions aren't just definitions of words. They're defined in this is what it is and this is how we measure it. That's the most important next step. So make sure you understand how the terms are being used. When you're asking questions about the natural world, we need to be both careful and specific about how we ask the questions, because not all hypotheses are equal. The more clearly defined your variables, the better. A variable is any attribute that can assume different values among different people or across different times or places, right? So variables in our situation is violent video games is one variable, right? Because you have a violent video game versus a non-violent video game. And then you have aggressive behavior as measured by level and duration of white noise that you give to somebody else, which is painful, by the way. When you see a claim made, make sure you understand how the terms are being used before you determine its validity or strength. In the video game example, aggressive behavior had a nice, specific operational definition, right? Level and duration of noise delivered to the opponent. Okay? This helps clarify the scientific hypothesis that's being tested, which is viewing violent video games increases aggressive behavior. You can test this kind of hypothesis because of how you've operationalized its terms. So let's talk about hypotheses now. This sentence might throw you for a loop, so I apologize in advance, kinda, but it's important, so hear me out. The goal of research, the goal of scientific research, is to reject the null hypothesis. Okay, let that soak in for a second. Whether a hypothesis is used to inductively reason up to a theory, or it is used to suss out the details of a theory through deductive reasoning, it can be defined as, for the purposes of this class, a hypothesis is a proposed explanation that acts as a starting point for further investigation. In our example, the hypothesis again is viewing violent video games increases aggressive behavior. And get this, if you craft a sentence that is the exact opposite of your hypothesis, it would be called a null hypothesis. And as confusing as it seems, the goal of research is to reject the null hypothesis. That's right. Contrary to popular belief, scientific research doesn't prove anything. The goal of scientific research is to provide evidence for either supporting a hypothesis or rejecting a hypothesis. And another way, the criteria of supporting a hypothesis is rejecting the null hypothesis. I know, it's a double negative. You're taking the thing that you're saying, you're making a negative out of it, and then you're saying, I want to reject the negative version of the thing that I'm saying. Even if you don't understand exactly why, please understand that this is based on logic. Like literally based on the philosophical branch of rhetoric that logic falls into. So using the video game example, the null hypothesis would be it is not the case that viewing violent video games increases aggressive behavior. And the goal of research would be to reject this null hypothesis by providing evidence for its statistical improbability. I'm going to talk about that later, but I'll say it again. The goal of research is to reject this null hypothesis. How? By providing evidence for its statistical improbability. I understand this is confusing, again, with the double negatives, and I won't dwell on it further, but it is a distinction that makes a difference and a point worth memorizing. The goal of scientific research is to reject the null hypothesis. Okay, so we're starting to talk about theories now. We've talked about inductive and deductive reasoning before when we talked about the history of psychology. In talking about Plato and Socrates, they believed that knowledge was essential and those laws, those universal laws already existed, and we just needed to look inside ourselves, tap that part of our soul, and then deduce the meanings of specific events. Whereas Aristotle used inductive reasoning, showing that specific examples should be the starting point that we use to build a universal law out of. And then after that, you could deduce from that law. So it is a circular process. And that's kind of the point that I wanted to bring with this infographic on the side with the circle. Science is usually a process of inductive and deductive reasoning happening in a cycle. When you observe something new, you use inductive reasoning to try to build a general rule. And then once you've demonstrated that general rule, you can use it to deduce predictions about other specific events. And then that'll just build strength for the theory and hypotheses derived from that theory. So you can tell from what I just said that hypotheses are what theories are built on, and a theory is the gold standard of science. The gold standard. It's true. So theories are the gold standard of science because why? Of their explanatory power. There's that. Through the process outlined earlier, where hypotheses inductively generate theories that deductively generate hypotheses, whose results change the theory that change the hypotheses, etc., etc. This nice cycle happens. Scientific theories slowly become refined and self-correct over time. Scientific studies that test hypotheses prune unnecessary parts of a theory while keeping and updating the thriving parts, thus resulting in a theory that has maximal explanatory power, which is just a fancy way of saying it explains a majority of the things that we see. It doesn't have to explain everything that we see. That would be nice. But it does have to explain a majority of what we see in a reasonable way. The power of any theory is its explanatory power. Okay. So to be clear, a scientific theory is more than a guess. Even though the terms theory and hypotheses are used interchangeably in regular conversation, just as science is the gold standard of providing natural answers to natural phenomena, theories are the gold standard of science. For the purposes of this class, a theory is going to be defined as an explanation or model that fits many observations and makes accurate predictions. Right? And those are just two different criteria of explanatory power. Just as not all hypotheses are equal, not all theories are equal. For a scientific hypothesis to be useful, it needs operational definitions of variables to make it worthy of research. Well, what makes a good theory? A good theory starts with as few assumptions as possible and leads to many correct predictions. In that way, it reduces the amount of information we must remember, bringing it down to its essence. Beyond that, we'll go over 3 specific criteria for a good theory. We're going to start with falsifiability, or showing what evidence could count against a theory. We're going to move on to burden of proof, which is the obligation to show evidence to support a claim. And then the other is parsimony, which is another way of saying all things being equal, we prefer simpler explanations. Let's talk about falsifiability. The philosopher Karl Popper emphasized scientists' willingness to disconfirm their theories by saying that the purpose of research is to find which theories are incorrect. That is, the point of research is to falsify incorrect theories, and a good theory is one that withstands all attempts to falsify it. I know this kind of sounds like double negatives again, and I apologize for that, but you just bear with me. A well-formed theory is falsifiable. That is, it's stated in such clear, precise terms that we can see what evidence would count against it, if, of course, that evidence existed, right? Something can be falsifiable and not yet falsified. A theory that makes no definite prediction is not falsifiable. For example, Freud's psychodynamic theory. It was eventually used to account for every human behavior under the sun, from religion to humor and beyond, right? But it never applied to Freud somehow. Sometimes a cigar is just a cigar. Give me a break. Trapdoor. Anyway, Freud even had a theory for disbelievers. He would just call that resistance. So there was no way out of his web. If you believed it, good. If you didn't believe it, the theory accounted for that disbelief in its own mini theory called resistance. Can you imagine any evidence against such a view with such an obvious escape hatch, a little trapdoor? If not, it doesn't qualify as a good theory. Moving on to burden of proof. Burden of proof is the obligation to present evidence to support one's claim. In science, the burden of proof is on anyone who makes a claim that should be demonstrable, if it's true. For such a claim as, like, UFOs from outer space have visited Earth, or ghosts exist, or some people have psychic powers to perceive things without any sensory information. The burden of proof is on anyone who supports these statements. If they're true, someone should be able to show clear evidence. And again, through testing and research, that evidence is shown as being able to reject the null hypothesis. Excuse me. Moving on to parsimony. Drink a little seltzer here. Black cherry seltzer. This portion of the lecture is brought to you by where do I go? Giant's Black Cherry Seltzer. Crisp and refreshing. All right. When given a choice among explanations that seem to fit the facts, we seem to prefer the ones whose assumptions are fewer, simpler, and more consistent with other well-established theories. This is known as the principle of parsimony, and the story of Clever Hans is an example of using parsimony to reach a simple explanation to a novel event. So the picture that you see in the background of this slide is Clever Hans. Hans is the name of the horse. And the story goes like this. So Clever Hans was a horse, and its owner claimed that it could do math. And all it would do is just ask questions like basically like, hey, Clever Hans, what is 1 + 1? And it would stomp its foot the amount of times that was supposed to be the answer. And more often than not, it stopped at the right number of whatever the math was. And the math became more and more complicated as these demonstrations occurred. Now, keeping in mind that Clever Hans was like a phenomenon from like the 1800s, you know, like people were wondering whether horses could do math. Okay, I just wanted that to sink in. So they were literally questioning whether or not Clever Hans had the ability to do arithmetic. And considering that there is no theory to account for horses doing math in this manner, it wasn't congruent with other well-established theories. A simpler explanation, instead of thinking, oh, what's happening is this particular horse is an anomaly to everything else that exists because it can do the thing that no other horses have been demonstrated to be able to do, which is math, and somewhat complex math. Either that or something simpler like its owner knows the answer and gives it away by accident with tells. And horses are known, especially trained horses, to be very vigilant of their owner's cues and tells. So after some experimentation where the owner was put out of view of Clever Hans, demonstrating that when Clever Hans had nobody to look at and no cues as when to stop clomping its hoof, it would just keep going, right? So it wasn't that Clever Hans was doing math. Its owner was doing math, and Clever Hans was just picking up on the cues of the owner to stop the counting at the appropriate number. Excuse me. So even though that sounds complicated, it's much less complicated than a horse that can do math, right? You have to do mental gymnastics to make room in your brain hole for a horse that does math in a way that you don't, acknowledging that horses pick up cues from their owners. And we're not even saying that the owner was doing this nefariously or maliciously or on purpose. He could have just been doing the math in his head and just was giving away tells. So, parsimony. Rock on. So, you might protest. Shouldn't we remain open-minded to new possibilities? Well, yeah. If open-mindedness means a willingness to consider proper evidence, but not if it means the assumption that anything has much a chance of being true as anything else. That is not keeping an open mind, right? Keep an open mind, just not so open that your brains fall out. So, a parsimonious theory that can be falsified, but is currently unfalsified, and has met the burden of proof by presenting valid evidence for claims, has strong reasons to be trusted as a theory with explanatory power. This is a good start. With this basic and bookish understanding of theories and hypotheses, we can start talking about research. So let's begin with the main subjects of psychological research: human beings. You take samples of populations. Okay. A population is the broadest category or group of people you are trying to target. And since we can't test every person in a given situation, we have to settle for a small portion of them, or a sample, or a small group of people meant to represent your target population. This assumes that your sample is representative of the target population based on certain variables, and that's a problem worthy of its own class. But general problems with sampling aside, let's look at how to resolve them through different methods of sampling, different sampling methods. Researchers who expect the results to be about the same for almost everybody in a population can use what's called a convenience sample. And here, a group is chosen because of its ease of study. I can personally attest to how this form of sampling provides the fastest way to recruit because it is a first come first serve type of sampling that allows for quick and convenient recruitment of participants. What's the downside? It lacks the integrity of a random or representative sample. What if you don't expect the results to be about the same for everybody? Well, fear not. You have choices, but they're not as convenient to recruit. And so now we have more restrictions and more obstacles. The more restrictions on your sample, the more intensive the recruiting process can be. So moving on to the representative sample. A representative sample is one that resembles the target population in proportion of ethnic groups, age, or whatever characteristics seem likely to affect your results. To get a representative sample of a target population, an investigator first determines what proportion of the residents belong to each category of interest. And then your recruiting should match those proportions. Of course, a sample that is representative in one way might be unrepresentative in another. So if you want to hold your sample as representative of more than one variable, you're making it more and more difficult. A random sample. Random sample is one in which every individual in the target population has an equal chance of being selected. A random sample has this advantage. The larger the random sample, the smaller the probability that its results differ substantially from the whole population. So random samples are good, especially large random samples. However, while a random sample is theoretically the best, it's pretty difficult to achieve. Moving on to a cross-cultural sample. Cross-cultural samples contain groups of people from at least two cultures. So it's pretty easy, literally tells you what it is. Cross-cultural sampling is difficult because of the expenses, the language barriers, and sometimes the reluctance of people in some cultures to participate in unfamiliar tasks. So here's a little summary of the different kinds of sampling methods, right? So if I were taking notes, I would summarize convenience sampling as who's available now, and representative sampling as representative, represents the population. The random sample is an equal chance to be chosen, and cross-cultural is at least two cultures. All right. So going to the example, the video game example, who is the sample that is being tested? Well, according to the little blurb in your textbook, it is male and female undergraduates from Iowa State University. I have questions about this. Is this a biased sample? Could it be the case that the males and females that are undergraduates at Iowa State University maybe don't really reflect the general population? So it makes you wonder. The results of a study that only used this sample, it can definitely be said to apply to the males and females at that college. My question is, do you have a leg to stand on to justify saying that these results are representative of the whole population? Is the student population of Iowa State University representative of the population of the United States? Or even the state of Iowa? These are the kinds of questions I want you to think about. Okay. Assuming we've chosen our hypothesis, our target population, and our method of sampling, we need to next determine what kind of data we're going to collect and what instrument we'll use to collect it. That is, how are we going to collect data? And those are the questions that get answered when we talk about research methods. That's where we will pick up in a little bit.